Okay, welcome back. Here comes lecture 2 of the series by Rama.
Thank you, Doctor. So whatever I was saying as what is the kind of situation, what we can find out, what we cannot, is still classification of three manifolds or classification of knots. Can you find a quantity that inequivalent knots have different answers for that quantity, which is what we call it as knot invariant? Unfortunately, at least from the known knot polynomials, it appears that it's still an open question. Okay, so these are the motivations why we want to go and see how Jones polynomial can be obtained. So I'm going to say that these are like ambient isotopy invariants, which are like Jones polynomial. And Jones polynomial, there is a procedure of obtaining the Jones polynomial. Okay. So the procedure is that in any region of the knot, just focus on a specific crossing, which is an over crossing. Okay. You can put orientation on the knot. So in fact, once you put an orientation on one strand, rest of the things are fixed. You have no control on it. So this is like an overcrossing. The remaining regions I am not touching. There could be some regions. And what I am going to concentrate on a particular crossing. And if this particular crossing, usually if you put a forefinger on an overcrossing and see whether the thumb points in the direction of the crossing or not, then that decides for you the right. Okay. For example, the right for this crossing is, you see that the arrow is pointing in the direction opposite to the direction of this. So I would say that this is a negative kind of right. Okay. So some of these things you will see in many knot theory books, that they'll say they would have had a 5 crossing knot, but then if you go and count the right, like figure 8 for example, there will be 2 of them with right plus 1 and 2 of them will be with right minus 1. They will add up to give you a 0. Okay. So trefoil will have a right, you can have a trefoil with right plus 3, and the mirror image of the trefoil, which is usually denoted as T star, that will have, what will happen? If I just make this crossing into a mirror image, what is it going to be? Right? What is the nature of this crossing? Over crossing, I have to put a forefinger, and it is right is plus 1. Correct? The mirror image is what will give you whatever was over will become under. So the right changes by a sign. So trefoil, if you take the knot, trefoil, and make all the crossings, over crossings into an under crossing, you get a mirror image which is T star, and T star mirror image, the right will become minus 3. Yeah? So these are what we call it as chiral knots. And T is not equivalent to T star. That is the meaning of chiral knots in general. K is not equivalent to K star. Not equivalent in the sense, when you're doing readmaster move 1, 2 and 3, you will never be able to go from one knot to the other. So they are mirror images of each other. Okay. So this is one. And figure 8, in the Rolfson table, figure 8 is denoted as 4 crossings, and this is a sub-index where there is only one particular knot with 4 crossings, which is what we call it as figure 8. This figure 8 knot, the right is 0. Okay, you can count now drawing the diagram, you start with an orientation and complete the diagram. That's an exercise for you. And you can show that the right is 0. And you can also show that 4-1 star is same as 4-1. Is equivalent. To draw a mirror image of it, where it must move 1, 2 and 3, you can go to the mirror knot. Okay. So in that sense, it is what we call it as achiral or ampichiral. Okay. Fine. And for all these evaluation, we are going to concentrate on a crossing, which is an overcrossing, and then we make that overcrossing into an undercrossing, and based on these arrows you can see the no crossing has to be of this type. Okay, right? If you see the arrows here, arrows went from here, so this is the no crossing diagram. And you will have to write a kind of a recursion relation or skein relation. Okay. So you start relating the Jones or whatever the Jones came up with the procedure. Where you have a Q times V of a specific crossing okay. So you try to use this recursion relation. So let's do a simple example. Let's take okay. Is the arrow okay? Yeah. Fine. Let's work out this. Since it's ambient isotopy invariant, this invariant should be same as an unknot. This invariant will also be same as an unknot. Correct? And then you get okay. In Jones' work, he started with taking the unknot invariant to be 1. Okay, so he took the unknot invariant to be 1 and then he showed that so this turns out to be, so if you assume V of C unknot to be 1, that is Jones polynomial for unknot is 1. Okay. So if you assume that, then you end up getting unknot squared. There's some slight issues about sign, but I'm not really worried about the sign, overall sign, but this is what you will get. Okay. And you can proceed this way, even though I've drawn it for a specific simple case. You can start doing more cases, right? You can start doing situations like a connected sum of A with connected sum of B. Okay? You can start writing 2 times V of this. You can put a, okay, minus Q inverse times V of this. So these are some arbitrary rooms which I can have. V of no crossings. Okay, you can draw it as okay. This is nothing but you can undo things, right? So you can show that V of correct? So what does this show? Connected sum is like the Jones polynomial of a disjoint a link, right? Divided by V of is that right? Or Q per half plus Q per minus half. Right? So there are some small conflict when we do in the quantum field theory, keeping this to be normalization to be 1, we will see that now, and we are forced to normalize it by a normalization n. So we would like to take this to be n, and we would want V of this to be n squared, and V of this to be n cube, and so on. Okay. So if you want to achieve this, then we are forced to make this consistent with this. We would like to write in field theory we'll come to how these things are computed in field theory. Before I get to that, I would like to make a slightly change of normalization of the Jones invariant. So let me call it as normalized invariant for the knot, for the unknot, minus half, and therefore V of connected sum B will turn out to be V of A, V of B. These are all normalized, okay? Okay, so this is one modification which we do when we go to field theory, and anything which is involving objects like this, okay, so this is all important in my, these are normalized, okay. So this is very, very important that I need to make a slight change when I go from physics to mathematics. One of the reason is that I would like it that any object, if I take a piece, I would like it to be whatever is that normalization, I want that to be. If it is 1, it becomes kind of contradicting when I do the recursion relation. For 2 copies, I get some answer. I want everything to be the same, so I use that normalization changed this way. Okay, not mine, but this is the convention that is followed. Okay, many times people will see the field theory answer not matching with the Jones table, and you have to divide it by the unknot, because there the unknot is 1, so you have to divide it by the unknot value to match with the knot tables of Jones polynomial. Okay, so that is 1. Now we would like to prove. Okay, using formal field theory notations. Okay, and what I want to say is that the skin relation is complete. So I have tried to show you that I can get the unknot invariant from here. You can start doing with the Hoff link. Okay, and one of the crossing, if you make it into an undercrossing, it will give you 2 unlinked unknots, right? And then if you make it no crossing, you get just the unknot. So can you work it out and see what you get for a Hoff link? Okay, so please work it out and see what you get. And that will give you, if you assume V of unknot with this normalization which we would like to do, you will get the normalized Hoff link answer. You are going to use that unknot squared as the polynomial will be a product of the normalized unknot polynomial, and similarly unknot, and you can work it out. Okay. Once you have the half link, you can go to trefoil, and then third crossing you make it undercrossing and relate them, and you can get the Vn of trefoil. Okay. Fine. Is the procedure clear? Yeah.
I have a question with the Hoffman. So, if you take, like right here, if you take for links, you take the linking number, which should flip with the mirror image, right? So, linking number goes to minus negative linking number.
Yeah.
But the Hoff link is amphichiral. So, the linking number
Hoff
1.
link is not amphichiral.
It's not?
No.
So is it not ambient isotopic to the same one? Okay.
H and H star are, Hoff and Hoff link star are different.
So you cannot deform one to the other.
The way is, if you had one loop and another loop with the current going in the clockwise direction, if you change the other loop anti-clockwise, you will not get it to be same. You will not, by any amount of Friedman's term, you cannot make that current to reverse that. Okay, that's H star.
But it's only if you switch the direction of one.
Yes, if you do simultaneously, then yes, but you can't do both. Yeah. So that also tells you that since you have brought this in, so I will say that every knot, okay, you can draw it as every knot or a link, you can draw it as a closure of brains, okay. So if you take trefoil can be seen as a closure with 1, 2, 3 half twist, and then you close it. Okay. Hoff link, you can see it as closure of 1, 2. Okay. So here you can see that I can use a different color. So this color I can change it to, okay, and I put crossings of which are both are parallel. Okay, these two relative strands are going in the positive orientation. I can do this, and what he's saying is that if I take the mirror image, So here when we do for trefoil, it's just if I start from here, I end up coming back to this point. Okay. But in the case of half link, if I start from here, I will only partially trace this white color loop and then the separate thing. So what you can see is that if it is parallel orientation, okay, here mirror image, if I do, then the right of this is what? Somebody can tell me? Right is positive here. And then if I take a mirror image, right will become negative. But for the links, there's no point in talking about right. Right between components is meaningless. Right within a component is having some meaning. Okay. So here, within this component, it doesn't have a self twist at all. Whatever half twist it has, it's between the two components. Correct? So you have to define what is a linking between these two components. So the linking is defined as half of the right between the components. So right between the components is plus and plus. So you will have 1 plus 1, which will give you a plus 1. So this is what we call it as a linking number between component 1 and component. There are only two components here. So usually it is said half link has a linking number plus 1. His question is, you make a mirror image. If you make a mirror image, what will the linking number become? This is half. Half star will be the mirror image. If you draw a mirror image, then overcrossing becomes undercrossing. So then it becomes negative, right? Half of minus 1 minus 1. Are you all with me? Then what will that give you? Minus 1. Okay. And whatever it must move you want to do here, it's very difficult for you to make that overcrossing to become an undercrossing by changing this linking number. Okay. It's very difficult. It's or equivalently H and H star are inequivalent. This is one way of drawing. In the context of links, I could have drawn slightly differently also. I could have drawn not looking at it as a closure. So this I called it as closure because I had a 2-strand braid. After I've done the crossing, I identify this end with this end. I identify this end with this end. Okay. And I take this crossing happening on an oriented, upward oriented strand. Okay. But equivalently, half link I could draw in a slightly different fashion. I could have an anti-parallel strand. Okay. This you cannot see it as if it is going in time in one particular orientation. You should see it as two anti-parallel strands are given. They undergo crossings. Okay. So let me take this as a crossing. Okay. And then I identify. So it's in fact the way they would do this is that they will call it as a Platt diagram. Okay. What does Platt diagram mean? That arrows are matching, right? Okay. So this is what you call it as a Platt diagram, where here what is the right or the crossing signs? It's negative, right? It's negative. So this should be actually, because the linking number is minus 1. Okay. So the same parallelly oriented strand, parallelly oriented mirror image if you draw, or if you draw anti-parallel but a Platt diagram, these two are one and the same. Okay, these two are one and the same. This is same as this one. Okay, so some of these equivalents of the diagram either drawn as a closure of a braid or as a plait diagram, or sometimes you use plait here and a closure here. Those are also possible in some situations. So those are called quasi-plait diagrams. Okay, so for example, figure 8, 4-1, you can, and then you can have a okay, so you can draw a, sorry, and here you could do something like this. Okay, so you can draw a diagram of this type and you can show that it is neither a closure nor a plait. Closure means all of them have to be parallel. There is a closure diagram for 4-1 also. The 4-1 closure diagram will be involving a 3-strand braid, and then you can draw and then you can do a closure. Okay, identify this with this, identify this with this, identify this with this. You can do that. But all of them are going parallel. Okay, so this is a closure diagram. But this closure diagram involves closure of a 3-strand braid. This closure diagram involves closure of a 2-strand braid. But the same half length, which is a closure of a 2-strand braid, I can also equivalently draw it as a 2 anti-parallel strands where there is no meaning in talking about closure. It's a plait diagram. This diagram by Readmaster move 1, 2 and 3, you can make it look like this. Okay, and this diagram is what we will call it as a quasi-plait. It's not a closure, it's not completely a plait, but you can make it as a diagram with some kind of a mix and match where you can see that including the closure points, there are only, at any slicing if you do here, right, you see that 1, 2, 3, 4, 5, 6. Here at any point if you do a slicing, it is intersection is 1, 2, 3, 4. So this diagram has 6, but this one if you try and do it anywhere, any slicing, you get 4. Okay, so what our aim was always, any complicated closure of a braid becomes, it involves more and more complications, and we wanted to confine to a situation where we can redraw it as if it involves only at any point if I take a section, that section intersects this at 4 points. You understand what I am saying, right? I can take a horizontal plane intersecting this knot, and then you see that on the plane there will be 4 punctures created. Okay, so this is what was the aim of redrawing a closure of a braid as a quasi-plait diagram as much as possible. We wanted to keep the quasi-plait diagram to have only 4 punctures. Okay, some are possible. So this allows us to play around one side in an algebraic quantities, in the other side also to see explicitly Readmaster move 1, 2 and 3 can give rise to this. Means if I work out by this method, I will get an answer which should match this one because they are related by Readmaster move 1, 2 and 3. Okay, so a lot of equivalence helps us to fix many of the algebra. You will see that these were some things which you saw from the recursion relation, and many of these things will also fit in a field theory argument. Okay, so this is all for I assume all of you know braids are You know, you can view the braids like a way on a plane. You can take two particles sitting on a plane. If you are going to confine that you are on a plane, the exchange between these two particles, there are only two possibilities. Either the exchange can be clockwise or the exchange could be anti-clockwise. Okay? But if you go to 3 dimension, if you allow the third dimension, you can use the third dimension, right? And flip this. You can flip it. What does it mean? Clockwise exchange is equivalent to an anti-clockwise exchange in 3 dimensions. Okay? Whereas a clockwise exchange cannot be, by any move, cannot be made into an anti-clockwise exchange in 2 dimensions. If you live only in 2 dimensions, the clockwise exchange is distinct from an anti-clockwise exchange. Okay? And when we say that the clockwise exchange happens at t equal to 0, we draw it on the t plane at 0. We say that particle 1 and particle 2 went through a clockwise exchange. Okay? Let's say at t equal to 1, particle after that clockwise exchange at t equal to 0, at t equal to 1, let it undergo. After that it is traversing same. It is undergoing anti-clockwise exchange. What does it mean? I can put it as the opposite. Why? A clockwise followed by an anti-clockwise should be giving me an identity operation. Diagrammatically also you can see that this is nothing but it must move 2. I can remove it out. Okay? This is strictly in 2 space evolving in time. But if I take it to be 3 space, then the braiding, so let me call it as B1 for this and B1 inverse for this. In 3 dimension, B1 equal to B1 inverse. Agreed? B1 is for clockwise exchange, B1 inverse for anti-clockwise exchange. If you go one more dimension, you can flip it. What looks clockwise can be made look anti-clockwise. So what is this group? B1 equal to B1 inverse, you all know. In exchange of permutation group, exchange of transposition, always satisfies B1 squared equal to identity, right? This is just a group of permutation, right? In 3 dimensions, braid group becomes just a permutation group. It's only in 2 dimension, 2 space and 1 time. And if you Euclidize the time, then you get 3 dimension non-trivial curves in 3 dimension. That's where the braids play a very important role. B1 is not same as B1 inverse. Right? B1 squared is not identity. That is why B1 cube gives me a non-trivial knot. Clear? Okay, so this is the procedure. So what I've tried to tell you is that Jones polynomial recursion relation and any knot can be drawn as either a closure of a braid or as a quasi-plait of a braid. Okay, so now I'm going to get into Chern-Simons theorem. Any questions?
For any 2-component link, would it be true that if it's achiral, if it's amphichiral, then its linking number would be 0? No.
Linking number can become 0.
No, but would it mandatorily become 0? Because otherwise, if it's amphichiral and it flips, the linking number goes to negative. But if they are the same diagram, how does
So
this resolve?
typically amphichiral knots will have a should have a linking number to be 0 at least. Because you have to take a mirror image. All the overcrossings becomes an undercrossing and the right will change. I won't change the orientation. If you do both, then you do nothing.
So in general, all amphichiral links, like two component links, have 0 linking number. What's the first non-trivial example of an amphichiral link?
Whitehead link. Whitehead has a chiral, right?
It's chiral.
Yeah. But you can, I am not able to recall in the classification, but we can figure it out. Whitehead is also a not amphichiral.
Yeah, it's chiral.
Yeah. We can see it. Yeah. Yeah, but why are you specifically asking about amphichiral? There is some specific amphichiral thing which plays a role somewhere.
Yeah, that's just something I was doing. So that's why.
Sure. Okay. Yeah. Okay. So let me now get on to Chern-Simons. Okay. So this recursion relation which is written. So this was Witten's work. So first of all, if any of you are not following any of these formal quantum field theory, don't worry. I'm not going to go into the. I'm going to give you the working knowledge of how to reproduce Jones and other polynomials. Specifically, any field theory, if you start asking any physicist, they will give you an action. Okay. So the action will have a coupling constant. And you will also write it as some kind of a volume form or a 3 form on a 3-manifold. Okay. So all my lectures are going to be on 3-manifolds. I'm not going to put M3, but this is like a 3 form on a 3-manifold. And once I write this in an explicit fashion, which is explicitly metric independent. Okay. So I try to write this as if that you will have a epsilon, you can write this as an ADA plus 2/3 A wedge A. If you try to write these explicitly as, write it as A mu dx mu for A. These are called the gauge connections or gauge fields, and you can also introduce saying that the particles are not like your, in the electromagnetic field, they are just, they are not matrix valued. But if you are looking at strong forces or nuclear forces, they can become matrix valued, and those matrix valued you can put in with. So the way to see this is, in simple case, suppose I write polymatrices. Sure, polymatrices, many of you will know. Sigma 1 is 0, 1, 1, 0. Sigma 2 is 0, minus I, 0. And sigma 3 is 1, 0, 0, minus 1. If you take this, you can write this out explicitly as A mu 3 minus A mu 3, A mu 1 minus I A mu 2, and A mu 1 plus I mu 2. Okay. So this becomes matrix valued, and these polymatrices have some nice property that if you try to write the algebra involving sigma 1 plus or minus I sigma 2 and sigma 3, they are related to, and you can also show that sigma 1 plus I sigma 2 with sigma 1 minus I sigma 2, these are the Lie brackets, and you can show this to be twice. There may be some factor of these two, but this is the algebra it satisfies, and these are called the SU2 Lie algebras. Okay. So I'm just trying to give you a feel that you can either write them to be not belonging to that group, you can take it to be U1, then they are just numbers. If they are numbers, then these people, this wedge product will turn out to be 0, okay, for U1. And this is non-trivial only when you go to the other gauge matrix valued like SU2. Okay. So this is the starting point. In any field theory, any course in quantum field theory, we first start with an action. Then comes the partition function. Okay, so the partition function depends on the manifold M. And this partition function formally will involve the space of all possible. So you can find for this the equation of motion. Okay, so I'll leave it to you to extremize this action, set it to 0, and then that will give you F, which is dA plus A wedge A, this to be 0. Okay, so this will give you the solutions of allowed A's, classical solutions, and those solutions are called space of flat connections. Okay, so this is what we call it as a space of flat connections. So when we do the Z of M, we write a measure which is not very precise, but this denotes all possible gauge connection modulo gauge transformation. What is gauge transformation? For us in electricity magnetism, electric field and magnetic field are measurable quantities, but both can be obtained from, let's say, a vector potential a mu and an a mu prime. Both could give you the same electric field and magnetic field. These two will be related by what is called as a gauge transfer. Since it doesn't give me a new information, this space you have to divide by those equivalents. A and a mu are related by, so A and A prime are related by gauge transformation. You remove them. You just take one entry. Okay? You don't take everything. So this is what is the formal measure. And then we have an e to the power of is. Okay? So this is what I was trying to say in the morning. Should have information about the three-manifold. We call in field theory as partition function. For a mathematician, we would call this to be proportional to, up to some normalization. As I said, there is always a kind of slight difference, but an overall normalization. This will be proportional to three-manifold invariant, which is known in the literature as WRT or Witten-Resticke-Torayv invariant, and that should be obtainable from looking at a Chern-Simons field theory, where the action, as you can see, is explicitly metric independent. No metric at all. So which means if I draw a trefoil as a tiny small size or a bigger size, the metric plays a role. But metric is not there in the action, which means it is going to only capture for me the topology. It will not capture anything beyond topology. Okay, so it's metric independent. No notion of size or shape. You can squeeze, you can do stretch, as long as you don't cut and snap. Because you need cutting and snapping to go from this knot to some other knot. As long as you pull, push, change the size, it's metric independent, you will get information about the topological invariance in the theory. And one of the trivial topological invariant, which is going to be the main piece. The partition function is the main piece, and we start looking at observables which are correlators, which is going to be modulated by them. Okay. So in some sense, this has the information about Three-Manifold, and we will see how we can get the Jones invariant by putting observables in the field theory. Okay, is this clear? Okay, so let me stop at putting the observables and then we can come back after. See, none of these things are actually nicely explained. The braids, why it's so special in two space and one time. I had written one popular level article probably in 2001 in Resonance, where I've said that the exchange of particle in two dimension is special, especially for students who do quantum mechanics. They can see that the braiding is very non-trivial in two space, evolving in time. Okay, so you can take a look at it. So the observables which you have to work out, are the Wilson loop observables for any knot. So let me keep the trefoil. Okay. And since I'm working with SU2 group, I will put a specific representation. There is a Young diagram way of looking at a representation. The fundamental representation is denoted in the Young diagram language by a single box. Okay. So this evaluation we are going to do in the group which is SU2. Okay. So what is the requirement? If the field theory action is metric independent, I need this also to be metric independent, and this is given by exponential of path ordered, where this is done over the knot K or the trefoil for this case. Okay, and then you take a trace. Okay. Trace is because I showed you that the gauge connections are all matrix valued for SU2 and higher groups. So you need to take a trace. And this object is what will be explicitly metric independent, or also you can show that it's invariant under the gauge transformation mu going to mu prime. Okay? And it is this object whose expectation value formally can be written as so this trace is over representation R to be very specific, and if I put fundamental, then I put a fundamental. This representation, whatever I put, I need to take the trace. So if you put this to be spin 1, then the poly matrices have to be replaced by 3 cross 3 matrices, and then the trace is over those 3 cross 3 matrices. Okay, so that's the difference which you should know. And this so this is what will give you the expectation value, and this is going to be having info of T, the trefoil. Okay, so I'll say that, and it's a topological invariant. And claimed by Witten this should be the Jones polynomial of this one. Okay, so we'll come back to why the claim comes in the after the break, right? Is that okay?
Yeah.
I think 2 o'clock is the 45 minutes, right?
Yes.
Yeah, so let me keep track of it. Yeah.
You have some more questions? Okay, so let's have a break and we will start in 15 minutes.
15 minutes.
Yeah, so 20 past.